begin by looking at what is meant by the term fluid statics. Well, in terms of fluid mechanics, when we talk about this particular field of physics, we're really talking about a branch of mechanical physics that deals with fluids which are both at rest and also fluids which are in motion. Now, the term fluid is something which you've come across in everyday life in terms of your understanding of the term fluid in the sense of something which moves, which is a liquid which actually moves quite freely. Well, in physics, when we talk about the term fluid, we're actually referring to any material that can flow freely. Now, the term fluid actually includes gases as well as liquids. And so many students may find that difficult to comprehend at first, that you can have a gas which is a fluid, because they've always associated fluids with liquids. And so fluid mechanics is divided into fluid dynamics and fluid statics. So when we talk about fluid dynamics, we're really talking about a branch of fluid mechanics in which we study fluids which flow. In other words, we're talking about fluids which are in motion. Whereas fluid statics is in fact the study of fluids which are at rest. In other words, stationary. Now, another very important concept that we're going to look at in addition to fluids, in relation to fluids, is air pressure. And pressure is the effect of a force on a certain cross-sectional area. In fact, it is the amount of force that's applied per cross-sectional area. So one way of looking at this is to imagine, for example, that you're standing on a particular area in your room. So let's say you stand on an area which might just be, for example, 1/2 meter by 1/2 meter. And let's imagine your shoes fit entirely into that area. Then the pressure that you exert would be the force, which would be your weight, acting down on that area that you're standing on, which would be, let's say, for example, 0.5 meters by 0.5 meters. And so you can work out pressure just by dividing force by the area that the force is applied. So we can use this expression: pressure is equal to force multiplied by area. Now, pressure is in fact a scalar physical quantity, and the SI units of pressure are pascals. In other words, 1 Pascal is equivalent to 1 Newton divided by 1 meter squared. And pressure is the ratio of a vector force to a scalar area quantity. So a vector, for example, such as force, would have magnitude and direction, but a scalar function such as area would only have magnitude. Now, in terms of air pressure, we can talk about air pressure as being the pressure produced due to the weight of air which is exerted on a certain area or a certain surface. This is an interesting table because it shows you various densities of different materials, and it's important to actually understand the density of some substances, especially at atmospheric pressure, because we'll be doing density calculations as we study fluid dynamics and fluid mechanics. So here you can see, for example, that air has a density of 1.29 kilograms per meter cube. So on every meter cube, you have 1.29 kilograms of air which is acting on that particular surface. And then if you look throughout the list of densities, what you should notice is that the metals tend to have larger densities to some extent. than, for example, gases. And so this is quite a useful table, and we'll be using this quite significantly as we go through the unit on density and pressure. Now, at the beginning of this unit, we mentioned atmospheric pressure. And we also looked at the use of atmospheric pressure as one of the variables in the calculations that we've just been exploring in relation to pressure. So what exactly is atmospheric pressure, and what do we mean by the term atmosphere? Well, we're probably all familiar with the fact that the atmosphere is really the layer of air that surrounds the planet Earth. And the pressure that's exerted on the Earth's surface due to this weight of the atmosphere, this is known as the atmosphere pressure. Now, how do you actually go about measuring atmospheric pressure? Well, we can do this in a variety of different ways, but the most common one is to use what's called a barometer. And so a barometer is the device which is used to measure atmospheric pressure. There are different types of barometers, but the mercury barometer, well, this is an inverted or upside down glass tube. And this glass tube, it's inverted in such a way, in other words, it's upside down, and it's actually standing in a pool of mercury. Now, absolute pressure, sometimes given the symbol PA, this is actually the total actual pressure at a given point. And atmospheric pressure, that is the pressure of the surrounding air at the surface of the Earth. There is another type of pressure which is called gauge pressure, and that's given the symbol PQ. And this is the reading on the gauge which is equal to the difference between the absolute and the atmospheric pressure. So in other words, the absolute pressure, we could rearrange that and say absolute pressure is equal to the gauge pressure plus the atmospheric pressure. And we can say that the gauge pressure, that's equal to the absolute pressure subtract the atmospheric pressure. Now, we mentioned earlier how a barometer is used for measuring atmospheric pressure. And we mentioned that a barometer was a glass tube which was inverted inside a bath of a liquid, in this case, mercury. So this diagram gives you an indication of what a barometer could look like. And this is a specific type of barometer. This is one of the older versions. It's called the Torricellian Barometer. Now, at equilibrium conditions, the pressure outside of the tube, if you can imagine the pressure being exerted outside of this tube, is going to be equal to the pressure exerted inside the tube, or the fluid pressure. So the atmospheric pressure, which is the pressure of the atmosphere exerted downwards onto the liquid here, the mercury, that's going to be equal to the pressure exerted by the fluid inside of the tube, in other words, the fluid pressure. So at sea level, the average atmospheric pressure supports a column of mercury which is about 760 millimeters high. So if you were to set up this apparatus and have an inverted tube where there's a vacuum inside of that tube, and also inside the tube what you have is mercury, and you were to invert it so that the tube is inside a beaker of mercury, and you were to leave this tube inside the mercury bath or the beaker, and you were to leave it at sea level, then if you were to measure the height of that column inside of the tube, then the height of that tube would be 760 millimeters. So the height of the mercury inside of the tube would be 760 millimeters of mercury. And so what we say is that at sea level, that the column of mercury is going to be 760 millimeters high. And that's going to be in what's called a simple mercury barometer at 0 degrees Celsius. In other words, it has to be at standard temperature. If we change the temperature, then that height of mercury will change. So at 0 degrees Celsius, at sea level, then the height of the mercury is 760 millimeters. And this is called, in terms of the pressure exerted, this is called 1 atmosphere. Okay, so this average pressure, which is exerted, is called 1 atmosphere. Now, if we look at a little bit of mathematics at the bottom of this slide, you'll see that the atmospheric pressure, and we're going to call that the PF, because that's going to be equal to the fluid pressure. So atmospheric pressure, ATM, is equal to fluid pressure, okay, when we have equilibrium conditions. You know what pressure is? Pressure is weight divided by the area. So it's the weight of the atmosphere, for example, divided by the area of the contact that the weight of the atmosphere is having on the surface. So we know that weight can be expressed as mass times G, where G represents the force due to gravity. We know that weight is equal to m times G, and we can divide that obviously over A to give us the fluid pressure or the atmospheric pressure. Now we know that density is equal to mass divided by volume. So we can rewrite mass as equal to the density multiplied by volume. And what we've done here really is we've just used density is equal to m over v. So if we rearrange that expression, then what we get is m is equal to density times volume. So we're substituting mass with density and volume. So what we get is an expression for the atmospheric pressure, which is equal to the fluid pressure, going to be equal to the density multiplied by the volume multiplied by G. And that's the acceleration due to gravity, G. And that's all divided by A. So what we have now is we have an expression where we can now convert volume in terms of the height, the area. So if we say that the volume of the air is going to be equal to its height multiplied by its area, which is what volume is. Volume is height times area. Then if we do that, what you'll notice in this expression is that we can now cancel out A, okay, the area. So what we get there is an expression for atmospheric pressure and also fluid pressure has been equal to E multiplied by G multiplied by H. So if we know the height and we know the density, then we can work out what the pressure will be in terms of the fluid pressure as it relates to this particular fluid inside of the column, or the atmospheric pressure as it relates to the atmospheric pressure outside of that column at equilibrium. So this is another expression for atmospheric pressure or fluid pressure. Now there is a concept known as standard atmospheric pressure. So what do we mean by that term? What do we mean by standard atmospheric pressure? Well, in order to understand this, let us have a look at what is the value for that pressure. Well, standard atmospheric pressure is the pressure of the atmosphere around sea level at 0 degrees Celsius. And at 0 degrees Celsius, at sea level, mercury rises about 76 centimeters along the surface of the tube. So we can work out what is the atmospheric pressure at 0 degrees Celsius by using the expression that we've just derived, which is that the atmospheric pressure is equal to the density of the mercury in the tube if we use the barometer that we looked at previously, multiplied by the value of g, which is the acceleration due to gravity, multiplied by the height of the mercury inside of that tube in the barometer. So let's substitute in the values. We know that the density of mercury is 13,600 kilograms per meters cubed, and we know that the value for g, which is the acceleration due to gravity, is going to be equal to 9.8 meters per second squared. Now, we also know that the height of the mercury in the tube is 76 centimeters, which we've converted into meters, and that's equal to 0.76 meters. So the atmospheric pressure is going to be equal to 13,600 multiplied by 9.8 multiplied by 0.76. And if we cancel out all of the units, what we get is an expression which is that the atmospheric pressure is around about 1.01 times 10 to the 5 pascals. And remember, pascals is the unit for pressure. And remember what pressure is. Pressure is essentially force divided by the area squared. And so if we look at the values that we have in terms of pressure, then what we can see is that we have, for example, these will cancel out here. Meters and meters squared will cancel with this meter squared. So we're actually left with kilograms over second squared. So that would be equivalent to Pascal in terms of units. So we've just derived the atmospheric pressure using the formula that we derived, which was atmospheric pressure is equal to the density multiplied by G multiplied by H. And we've come to this particular figure for that atmospheric pressure. This is the standard atmospheric pressure. There are different types of barometers which are used to measure atmospheric pressure. And one specific type of barometer is called the aneroid barometer. And this is an instrument used to measure atmospheric pressure. But the only difference really is that this actually does the job of measuring atmospheric pressure without using any fluids, for example. It doesn't use mercury, it doesn't use any fluids, as in the barometer that we saw earlier on. Inside an aneroid barometer, what we have is a small capsule. And this capsule has had the air pumped out of it. So when the air pressure rises, the sides of the capsule, they're going to be compressed. But the capsule is then attached to what we call levers, which move a needle, as in this particular diagram here. You can see the needle here. It moves the needle as the air pressure squeezes the capsule. So remember, the capsule, it hasn't got any air inside of it. The air has been pumped out. So as a result of applying air pressure to the sides of the capsule, what will happen is the capsule will become compressed. And as a result of that compression, that dial will actually move. So the dial behind the needle, that tells you the air pressure and the altitude, or in fact the weather forecast. And this is quite a common barometer because it's able to tell you the three things. It's able to tell you air pressure, altitude, and or weather forecast. Another type of device which is used to measure pressure, and it's called a Bourdon pressure gauge. And this diagram shows you what the pressure gauge looks like. It really consists of a tube, and the tube is coiled into this kind of a spiral shape, or sometimes a helix shape. Sometimes you can see it's formed into what's called a C shape, as in this particular diagram. So what happens is that when the pressure increases, then this particular tube will actually begin to straighten out. So as the pressure which goes into the tube gets larger and larger and larger, then this particular tube then begins to straighten. This means that this part of the tube, as illustrated by the blue arrow, begins to move outwards. The tube will have an oval cross-section, as illustrated here, and usually one end will be connected to the pressure source, as illustrated here. So here you can see that as the tube itself increases in terms of the pressure inside of it, and as a result of that increase in pressure, it begins to straighten out, in other words, move in this direction, you can probably see what would happen to the pointer for the dial. You'll see that that pointer will also begin to move. So there is a direct relationship between the position of this dial and the amount of pressure inside of this particular tube, C-shaped tube. So the tube pressure gauge is usually attached to a pointing device, as we've mentioned here. And so that movement of the tube, just going from that position to that position, as it straightens out because of the pressure, that can actually be seen very easily in relation to the position of the dial. And so it's actually a very accurate measurement in terms of pounds per square inch, sometimes written as PSI, or sometimes the dials, the gauge themselves can have other measurement systems. So it may not be measured in pounds per square inch, but it may be measured in other units that can be used to measure atmospheric pressure or pressure in general. Now, another device for measuring atmospheric pressure or pressure in general is what's known as the manometer. Now, the manometer is in fact a U-shaped device, very similar to the one on the right-hand side of this particular slide. And it's actually used for measuring the pressure of gas supply. So this is more specific to measuring gas pressure, but it does use atmospheric pressure as a tool for measuring gas pressure. So the U-tube is filled with a liquid, as illustrated by this blue liquid in the diagram. Now, the important thing about the manometer is that it doesn't have any moving parts, and one of the good things is that it doesn't require calibration. So we can see that the pressure of the supply, well, that's going to be equal to the atmospheric pressure plus the pressure of the fluid. In other words, that's going to be equal to the atmospheric pressure plus, and we can write the pressure for the fluid as the density times G times H. So just to explain that equation in a little bit more detail, the pressure of the gas which is being supplied, so here we have the gas, and the aim of this manometer is to actually measure the pressure of the gas being exerted. And so the gas exerts a pressure, and we can call that gas the supply. And so that pressure is going to be equal to the sum of the atmospheric pressure acting on this particular part of the liquid plus the pressure of the fluid, which is also acting. And that pressure of the fluid is going to be equal to the density of the fluid times G multiplied by the height of that column of the fluid represented by H here. And that's going to be equivalent to AB B. So when you sum those two together, the atmospheric pressure plus the pressure exerted by the fluid, then the sum of those two will give you, or will be equivalent to, the pressure of the gas, because what will happen is that there'll be an equilibrium. So in other words, the pressure of the gas acting that way, in this direction, downwards, is going to be equal to the pressure of the gas acting downwards in this direction. And so the sum of the atmospheric pressure plus the fluid pressure, that's going to be equal to the gas pressure. So let's have a look at a few applications of air pressure. Well, air pressure is actually found in terms of the physics of drinking from a straw. When drinking with a straw, you have to suck the straw. So that's an example of the application of air pressure. And then there's a rubber sucker. When the rubber sucker is put onto a soft surface, usually a glass or a tiled surface, the air in the rubber sucker is forced out. This causes the space between the surface and the sucker to have lower pressure. And then also another example of the application of air pressure is in a siphon. A siphon is a rubber tube which is used to transfer liquid from a container at a higher level to another at a lower level. Another application of air pressure is in the lift pump. A lift pump is used to pump water out of a well or to a higher level. So when the plunger is pushed down, the lower valve closes and the upper valve opens, and then the water flows above the plunger. And then when the plunger is lifted, the upper valve closes and the lower valve opens, and the water flows through the lower valve. And we're going to have a look at examples of lift pumps in a moment in terms of a diagram. And a force pump is a device used to pump water through a greater height under the application of atmospheric pressure. And this is actually used by firemen. So in this animation on the left-hand side, this is an example of a lift pump. And it's quite an ingenious pump in terms of how it actually works. Now, if you look very closely at the pump, and in particular, pay attention to the valves here and here in terms of when they close and when they open. Now, when the plunger, which is the brown sort of rod here, when that is pushed down, what will happen is that the lower valve will close. Now, if you look carefully, you'll see that when this is actually pushed down, in other words, when that plunger goes all the way down, then you should notice that the valve actually is closed. Now, also what you should notice is that when that plunger is moving downwards, as well as this valve being closed, also the top valve is open. And that's called the upper valve. And that basically allows water to actually flow through to the top part of that particular piston. And so the upper valve opens, and that allows the water to flow above the plunger. Now, when the plunger is lifted, in other words, when the plunger goes up, then what happens is that the upper valve now closes and the lower valve opens up. And that essentially allows water to flow through the lower valve, and in other words, it fills that lower area. And so that means that when the plunger then goes down now, there's water in the lower area which can be used to fill the container. So this is just an example, a simplified example, but a very good one to illustrate in terms of an animation how a lift pump works. Now, a bicycle pump, well, this is really designed to inflate in many cases, and some of you may be familiar with this, in terms of bicycle tires. And so a bicycle pump is basically using the following processes to inflate a bicycle tire. And we're going to have a look at, again, at an animation to show how this works. But in terms of the processes involved, there is first of all what's called a upstroke. And in an upstroke, air flows in the pump from the outside. So in other words, you're actually pulling air into the pump. And then there's the downstroke. And in the downstroke, the pistons, they displace the air from the pump, and this goes into the bicycle tire. So when the above processes are performed, the bicycle tire becomes inflated. And you've probably seen this many times for those of you who have bicycles, but you've probably never thought through the process involved every time you use a bicycle pump. So let's now have a look at how a bike pump works. And this is just a short video which will explain to you the process involved in terms of an animation.
The bike pump is a useful piece of equipment that requires no electricity. Have you ever wondered exactly how it works? Well, in this presentation, I will show you exactly that, the mechanics behind a bike pump. To begin, I will first describe the different role each part of the pump plays in inflating a tire. I will then detail the 5 stages needed to pump a bike tire. In the first stage, the piston rises. In the second stage, air enters the chamber. In the third stage, the piston lowers, which in turn closes the inlet valve. In the fourth stage, the outlet valve opens, and finally, in the fifth stage, the compressed air inflates the tire. But before I explain these 5 stages, I will describe the parts of the pump. All bicycle pumps share several similar components. The first is the body of the pump, which is the outside of the pump. The chamber that stores the air inside the pump is referred to as the compression chamber. A hose is attached to the compression chamber and in turn is attached directly to the tire valve, connecting the pump with the tire. Inside the pump's body is a piston that moves up and down, compressing air into the compression chamber and forcing it through the hose into the tire. The piston is connected to a handle, which the user holds onto when pumping the tire. And finally, there are 2 one-way valves that are essential in the functioning of a pump. The first is the inlet valve, which allows air to flow into the chamber, but prevents it from flowing out of the chamber. The second is the outlet valve, which allows air to flow into the tire, but prevents it from flowing out of the tire. Both valves work in conjunction with the piston. Now that you are familiar with the separate parts of the pump, I will explain the 5 stages of how the pump works. First, to begin the process of pumping up a tire, the piston rises when the user pulls the handle. The rising of the piston draws air into the body of the pump. In the second stage, air enters the compression chamber. The inlet valve opens to allow this to occur. The air contained in the chamber is now ready to be compressed. In the third stage, the user lowers the piston, which closes the inlet valve. The inlet valve remains closed while the piston is being pushed down. This means that the air has no other way to flow but out of the hose and into the tire. In the fourth stage, the outlet valve opens. The built-up pressure in the chamber forces this one-way outlet valve open. And because it's a one-way valve, the air flows only in the desired direction, from the pump chamber into the tire. In the final stage, air inflates the tire. The compressed air leaves the pump via the hose and enters into the tire. inflating it more and more with each downward stroke of the piston. You now have a fully inflated bike tire.